Welcome back to the garage with Bob and I. It's May, it's freezing, but we're going to learn anyway. What the heck, we're here. Today we're going to look at another one of those little tiny discoveries that changed the whole world. It's unbelievable how something that small, if applied correctly, can make such a big difference in our lives. Now this is a galvanometer. You can see the meter in there, how it works. We have wire connected to it, just goes in a big loop, comes out and goes back down. Here we have a horseshoe magnet, and I want you to watch the needle as I move the wire through the magnetic field of our horseshoe magnet. Now watch that. You see that? See that movement? Bob, can you see the movement? Nod your head. He's not nodding his head. Okay, hold on, Bob. I think I can help you. Hold on a second. I've got a slightly bigger magnet here. Okay, let's try this one. Watch the... Can you see it now, Bob? Huh? Can you see it now? Yeah. There's no battery connected to this. We are making that amount of electricity just by putting this single wire through this slightly bigger magnet. And if we add to that what Ampere did with coils and solenoids, let's see if that makes a difference. Well, look at that. That's only 4 wraps of wire, and that seems to make a big difference. Well, now, if you notice in this case, I'm moving the conductor through the magnetic field, and we're making electricity. Well, let's go look and see if we can do it the other way around. We have to take a minute to get that one set up, so hold on a minute. Quick review. In the last segment, we showed you that if you take wire, even a solenoid like this, and run it through a magnetic field, you can produce electricity. Now we're going to show you the opposite. Okay, so we got to make sure you understand that. In one case, the magnet's moving. In the other case, the conductor is moving. Okay, we're going to show you that. All right, Bob, would you hand me a magnet over there? Cute, Bob. That's adorable, Bob, but that's not going to help. Hand me a magnet that'll work, Bob. That's a lot of fun, Bob, but that's not going to work. Hand me a bar magnet, Bob. Okay, I'm going to work better on my a bar magnet. There you go. Good job, Bob. All right, now get your fuzzy butt out of the way. All right, look. Here is a bar magnet, and we're going to run it through these coils and watch the needle on the galvanometer. Okay, here we go. See that? Look at that. Look at that movement. Now I'm going to do the same in this one. The only difference is there's more coils. More coils, more electricity, more deflection of the galvanometer. Look at this one. Isn't that amazing? Right, we're pegging the needle. We're pegging it. It's going bouncing off both ends. Okay? So you see the difference there. Now, let's go and look at this, the definitions, to make sure we got everything figured out. Thank you, Bob. Here, let's go through this written explanation to talk a little bit more about this electromagnetic induction that these two gentlemen discovered. Now, it's called magnetism makes electricity, electromagnetic induction. These two gentlemen are both credited with finding this a little bit before the Civil War, right around where Mr. McCoy started teaching. They both found the same thing. Hey, look, a commercial. What a great sport. A changing or fluctuating, going up and down, moving forth, magnetic field can produce an electric current in a conductor. And the world has never been the same again. Now, let's look at this a different way. Put that down there. Electromagnetic induction, the creation of an electric current in a conductor by a changing or fluctuating magnetic field. And you already saw that we can have the magnet sit still and the conductor move, or we can have the conductor sit still and the magnet move. Either way, as long as one of them is fluctuating or changing, you can produce electricity. So let's just review that real quick one more time. And then we'll show you some devices that actually use this. The key to this whole thing is this. Don't make it complicated. It isn't. is as long as one of the two, either the conductor or the magnetic field, is moving, changing or fluctuating, an electromagnetic induction will happen. For instance, here is a ridiculously old generator. You can see the magnets right here. And down inside of there, you can see the coils of wire. They're connected to this. Now, this thing does not work very well, but watch, it works. Watch. Luckily, I have some that work much better than this old antique. So, we'll set some up and show them to you. Thanks, Bob. I'm deferring to Bob's wisdom because Bob said before we show them the actual devices, maybe we ought to show them in a diagram how these things actually work. So we made some diagrams up here. This just happens to be copied out of a 1957 textbook. It was a fantastic year. Here is a magnet, so there's your magnetic field. Now inside of that is your conductor, and it's an armature. A lot of times there'll be lots of wraps of wire. And it's connected in this case because this is a direct current. It's got a split ring back here, okay? And this is called a commutator, just like a motor, okay? Here's your brushes, and as these turn in here, okay, that turns in here, this half the split ring touches this one, electricity's going that way. As this slides down around here, the green one moves to the top, the red one goes to the bottom. The electricity's still flowing in the same direction, but we've now flipped the wires, okay? That's how you get direct current. Edison really liked this, but it didn't work as well as it should have, and Tesla came up with this one. Now, the difference is not that great. Here we have, and this is an alternating current, okay? Same kind of things. We have the magnets, we have an armature, we have something cranking this thing, okay? In tonight's case, tomorrow's case, it's going to be Bob or I cranking the thing. This has two rings, okay? Slip rings, not split rings, but slip rings. And these are in contact constantly, and as this thing rotates, half the time the electricity is going that direction. When this flips over to here, this wire, the electricity will be going that direction then. So it keeps reversing. And this in the alternators, the generators we have here in America, that's going to change 60 times a second. Now, you don't really notice that, but it does. And that's basically the parts. Magnets, armature, the rings, brushes to collect the electricity, and that's it. Something to crank it. Something to give it kinetic energy. All right, Bob, let's set a few of these up. Bob and I have set up a cornucopia of generators here for you to look at. Some are alternating, some are direct current. The simplest one here is this. It's a coil of wire, little plastic tube. It's connected to these leads, which is connected to an LED light. I'm just going to drop these neodymium magnets down through there and watch what happens. See that? Isn't that amazing? Yeah. Magnets, magnetic, that's a changing, fluctuating magnetic field. And there you go. Isn't that amazing? Huh. Well, that's a very simple one. We'll put that aside. Here's another one I think you'll enjoy. Now these are called Gen Cons. And if you look at it, you can see the gears in here. There's the gears. I turn the handle. That's kinetic energy. That's mechanical energy. It's going to go in here. Electromagnetic induction. This little generator in there. If I turn the handle, you can see the bulb back there. Look at that. Isn't that amazing? Come on now. That's great. That's a handheld generator. Put that aside a little bit. Here's another one. I'm not hooking up this to a light bulb, but if you see this one, look at this. There you go. See the magnets there? And there's your two coils. Okay. Pull this handle. Now this one's got an added bonus. Get ready for this. Look at that. A sparkles on there, huh? Come on now. And when you push the handle, look at those sparkles. It's amazing. All right. Put that one down. Now you've seen this one. This is the older one. This is a heart attack inducing thing. It does work though. Now, the thing about this one is, if you accidentally or on purpose, like Bob does, put your fingers on there and turn that crank, you will get a more visceral idea of what the word stammer and twitch means. This sucker will light you up, so you got to be very, very careful with that one. Put that one back, or any electricity for that matter. Here's a different one. Now, if you see this one's very easy to pick out the parts on this one. See, right there are your armature. Okay, there's your armature. Here's your field magnets. There you can see the brushes on your commutator. Okay. Now that's using the slit ring, so this is going to be direct current. And I can make that bulb light up too. Now if you notice, in all these cases, either Bob or I are putting in the kinetic energy, which is changed to mechanical energy, which is changed to electromagnetic induction, which produces electricity, which gives you light and heat. In the large generators, this motion might be produced by water or steam, or a number of different things, geothermal, solar turning water into steam, any number of things like that. People who didn't, maybe a treadmill being run by people who didn't hand in their library books, you know, things like that. Something is turning that wheel. All right, there's that one. I'll leave another one to show you. Not so much the generator as to actually see a conversion of one form of energy to another. As I turn this handle on this GenCon, watch what happens to that one. I'm going to put them in the same orientation. See? So this puts them both together, both discoveries. Here we're putting in energy to produce electricity. Over there, we're using energy to produce motion. Back and forth, okay? So in one case, we're using a changing magnetic field to produce electricity, and over here we have the electricity to produce energy to make the handle move. So we're looking at both of them. If you notice, the two handles do not turn at the same speed because some of the energy is being converted. You can hear it into sound, into friction, into heat, into wires. So we're actually not losing energy, we're losing electricity. Okay, so it's being converted to other things. Okay, here's another version of that. Again, okay, here we go. Here's a generator. You can not so well see the parts in there, but that's a giant magnet on the outside, horseshoe magnet. The coils are inside of there. I'm going to turn this. In the first case, again, we're going to be changing a changing magnetic field producing electricity. The electricity is going to be producing magnetism, which is going to make that move. Here we go. Put that one down. Look at that. Come on. All right. In the next case, we're going to be producing, make sure I get this right. What are we going to do here? That obnoxious bell at the other end. Remember, electromagnets. Okay. And here we're going to produce light. All because of our generator. Isn't that amazing? Okay. There you go. A look at generators and conversion of electricity from one form of energy to another form of energy. This last generator that Bob and I want to show you is a little more complicated because you can get alternating current and direct current from the same exact motion. So Edison and Tesla, it's kind of putting both their ideas together at the same time. And the way they do that is, I'm going to zoom in here a little bit so we can show you some wiring so you can get this. If you look here, first of all, the direct current comes out of this. If you look, this one has a set of split rings. See both sides of the commutator there? There's your brushes, there's your armature, your field magnets. Now, how is this different than alternating current? In alternating current, remember, they have slip rings. So on this particular machine, the slip rings are over here and over here. So the same shaft draws split rings and slip rings. So let me put that lid back on there. And we're going to zoom back out if I can find the button. There we go. Move this up. I'm going to turn the crank, and see if these LEDs light for you. Yeah, they both light. Now to show you the difference between alternating and direct, I'm going to turn the handle backwards. Because if I go this direction, the electricity from the direct current goes through that light bulb in one direction. The alternating current goes back and forth. Every time you hear a click, it's going back and forth. What's the repercussions of that? Remember, this is an LED bulb. It only likes electricity. It'll only light up with electricity going to one direction. If I switch the direction of the electricity, it'll go off. You don't notice that in the alternating current one because there's enough electricity going through. Half the time it's going one way, half the time it's going the other. And so the bulb lights up half the time, but our eyes can't pick it up. So if I go this way, they both light. If I go this way, only the alternating current one lights up. And there you show a little bit of a difference between the two different alternating and direct current generators. I think it was a good idea, Bob. I guess we'll just go with an average. All right, here we are in our backyard. We've taken a compass and we've figured out that this is north and south, so we need to be perpendicular. We've got our conductor and extension cord, and we're going to twirl it in the magnetic field of the Earth, the magnetosphere, and we're going to see if we can get our galvanometer to work to measure if we got any current flowing through our wire. Here we go. Look at the movement. That's pretty amazing. That seems to work better that way. Ah. Isn't that amazing? Ah, how about that? Bob and I wanted you to understand another device that we have around all over the place. Look familiar? That's my iPad charger. We call them chargers, but in reality, they're really transformers. And there's two types. Step-up transformers, where you go from a low voltage to a higher voltage, or step-down transformers, which go from a high voltage to a lower voltage. And they only have 3 parts. It's really neat. There's no moving parts in a transformer. It's like some of our relatives. How about it, Bob? No moving parts. If you look at this, sorry. Here you have an iron core. Here comes the incoming wire, wraps around there. It's an alternating current, so it's fluctuating back and forth 60 times a second. As it does that, it produces a magnetic field. That magnetic field goes the whole way through the iron bar. Well, if you have a fluctuating magnetic field over here, you're producing a current in there. And that's exactly what happens. Electricity produces magnetism, magnetism produces electricity. And it just, in this case, since there are more wraps in the secondary coil, the voltage goes up. Now, if you look at the step-down transformer, that's the opposite. It comes in with many wraps and goes out with a few, so it's a step down. It goes from high voltage to low voltage, which is exactly what happens here. If you notice, you feel how dense they are? That's because of the copper and the iron in there. Here's another one that used to be like this. They came, all kinds of we call them wall warts, stick out from the wall. This one is from a microwave oven, and you can see, if you look closely, see the different wire? There's your iron, very heavy, very dense. This is the incoming, this is the primary coil, this is the secondary coil. Lots of wraps of wire because we need the voltage to go way up so you can make the magnetron produce the microwaves. See? It's heavy. That's heavy learning, Bob. Ah, it's a science joke, Bob. Get over it. I'm standing next to the big step-down transformers in Duncannon so you can hear them humming. That's 60 cycles a second. Here's another topic about electromagnetism that's kind of fascinating, very interesting. It's not really covered in your book that much because it is pretty in-depth, but we're going to take a look at it anyway. Oh, don't worry about Bob. Bob's doing fine. Bob just asked if he could go in the house and call his mom and dad because of the whole COVID-19 thing. He's a very sensitive guy, and he's reaching out, contacting people to make sure they feel good. And so we let him do that. This is okay. We thought it kind of symbolizes Bob a little bit. We're not going to get into that. Eddy currents. Now, these are pretty neat. It's involved with a thing called Lenz's law. When a magnet or a fluctuating magnetic field moves past a conductor, electrical currents are produced. All right, that's Faraday's law, okay, in the conductor. If it's got a complete circuit, they march along as electric current. But sometimes there's not a complete circuit, but they move out of the way anyway, and they kind of swirl around. And they make eddies, just like behind a rock in a stream. These currents produce a secondary magnetic field. This is where the whole Lenz's law thing comes in. That opposes the original magnetic field. So you have one magnetic field and an opposite magnetic field being produced by that secondary current that opposes it. And you get some very interesting interplay between these two magnetic fields. Let's show you a couple examples back here. Not Bob and I have a couple of devices here to show you to deal with eddy currents. Now, the first one is quite simple. We have a solenoid wrapped around this tube, and we have this little LED light, and I need something to prop that up with, so we're going to put these guys to good use for a change. And as I drop this down through, you should see the LED blink. Oh, look at that, it blinks. Thank God something works around here. Come on, guys. We need you to stay upright so we can see you. There you go. Now, if we pull this tube out and we insert this tube in, okay, now I'm going to drop the same neodymium magnet down through there. It's going to reach the same coil and it'll make the thing blink. Well, you're going to notice something. Could you guys please do your job? All right, here we go. See, it did blink, didn't it? Didn't it? But look how long it's taken to get down there. It's taken forever to get down there. And why? Because there's a magnetic field around this. Magnetic field going by a conductor, Faraday's law kicks in. And then what happens is that magnetic field produces a current in here. Well, that current produces a second magnetic field, which opposes the first magnetic field. And so what they're doing is butting heads, just like Bob and I occasionally. But that is eddy currents. Let's take another look at another type of display that shows you about eddy currents. Here we go. I love this thing. It's very, very simple. I'm very, very simple. Here you have a conductor. It's a very poor conductor, so we call it an insulator. It's plastic. Here we have copper, great conductor. We have aluminum. A lot of our huge power lines are made of aluminum because copper is too heavy, too dense, and way too expensive. So, look what happens when you drop these magnets, okay, down through here. Watch this. They're going to have a race to predict, hypothesize which one. Now, you think, what would affect this? Well, the better the conductor, the more eddy currents, the more opposing force, the longer it should take. So, did you notice? Not the same time. You could say this one won, but actually this one slowed down, so it did win too. If we put this one in the middle, let's see what we got now. Whoa, look at that. That really slowed down. To really see the effect of that, let's do the insulator and our best conductor. Look at that. Isn't that amazing? I find that amazing. Believe it or not, if you've ridden some rides at Hershey Park, that's what slowed you down. Eddy currents at the end, the braking like that. Here we have four of them. Copper, aluminum, brass, which is a mixture of copper and zinc, and another non-conductor called an insulator. And then we have these four identical magnets at the bottom. And watch what happens when I flip it over. See that? See how long it took for some of them to get down to the bottom? You would think they'd all fall at the same rate. They would, unless they're conductors. Some are better conductors than others. And that's why the eddy currents get built up in the ones that are better conductors, more, stronger, and so it slows them down even more. There you go. Well, we want to leave you with a little bit of something to think about. So here it is. Very simple, ridiculously simple. Two identical aluminum rings and a horseshoe magnet and a very old science teacher. But that doesn't matter. Immaterial. If I take this horseshoe magnet, which has a magnetic field, past this aluminum, okay, which is non-magnetic, and I go like this, Look at that sucker. I can get it to move. Woohoo! I'm not touching it, and I'm getting it to move. Ah, here's an identical ring. That would be identical, like the same thing. It doesn't. So you're thinking to yourself, self, can't be the batteries. They don't have batteries. So you flip it over and you say, all right, Mr. Knapp, let's, what if we reverse the magnetic field? Good idea. Still works. It's like some relatives, they still work. This one, on the other hand, nothing. And you know what? Sometimes in life you just got to think things through, figure it out for yourself. There you go. Have a great day. I'm going to check on Bob.